Welcome to the video on how to solve a stereochemistry problem using the model kit. This question asks, which of the following structures is a meso compound? Remember, a meso compound is a diastereomer that has two stereocenters that are actually mirror images of each other. So a meso compound is not optically active and it has a plane of symmetry. So basically this question is asking, which of the following structures have a plane of symmetry? So if we build the models and look through one at a time, we'll be able to see if these molecules have a plane of symmetry. So here is cis 1,4-dibromo cyclohexane, just like as in example 1. We have one bromine in the axial and we have one bromo in the equatorial, and it's 1,4-cis. So you can turn this molecule just as it is in the chair conformation and see that we do have a plane of symmetry going right down the molecule right here. Sometimes I think it's easier to see the plane of symmetry in a cyclohexane molecule if you make the flat ring. So if we build that flat ring, we see that we actually have two planes of symmetry, one going down this way and then another one that slices right through those bromines. So the first choice in our question, the cis 1,4-dibromo cyclohexane, is a meso compound. Now if we move to the second choice, it's this molecule right here, where we have our OH, which right now I just have represented as the red. So that's our hydroxyl groups. And then we have a methyl group coming at us here. And then we have a methyl group going away from us here. And then alternatively, we have a hydrogen coming at us here. And we have a hydrogen going away from us here. So I have built the model for that compound that's listed second on the question. So this is the model. The way that I start this off is I see in the plane of the board is an OH and an OH. So we build this first. And then we put our methyl groups and our hydrogens on accordingly. And so now, if we want to see if this molecule has a plane of symmetry, let's rotate the oxygens so that they're together, and we see that there is in fact a plane of symmetry in the molecule right down the center here. So this is also a meso compound. So if we look at the third compound, doing the Newman projection, where we're looking down the C2-C3 bond, so we see it here, and on the front carbon we have an OH going down, and on the back carbon we have an OH going up. And so then I have two methyl groups, one on the front carbon going to the right and one on the back carbon going to the right. And so here is our molecule. We have the two hydrogens going to the left. And now if we rotate our two hydroxyl groups to be in the same place, we see that our carbons and our hydrogens do not line up. So this molecule right here is not a meso compound. It turns out this molecule right here, if we put the hydrogen in the back and we give this an R or S value, this carbon right here has an oxygen. That's number priority 1. Then this carbon has an oxygen as well. So this is priority 2 and this is priority 3. So that is going to be in an S configuration. Now, if we look at the other carbon, we put that hydrogen in the back. We have 1, 2, 3. That is also in the S configuration. And so right here we have a compound that is SS. Therefore, it cannot be a meso. In order to be meso, we have to have SR or RS. They have to be mirror images of each other. Compound number 3 in this list is not a meso compound. And if we look at the last compound, we see that it is in a Fischer projection. And so here's how I build my Fischer projection models. Okay, so on that top carbon, we have a methyl growing back, And on that bottom carbon, we have a hydrogen going back. So we're going to rotate that. So here's the Fischer projection with these two being the crosses, this being the top, and this being the bottom. So there's our straight chain down in the Fischer projection. And now I have a bromine shown in green here, and a bromine shown in green here, and then over here I have a methyl group. So I have built the model of the Fischer projection. Remember, anything on the sides come at you, like the bromine and the hydrogen here, and the bromine and the methyl group here. And anything going up and down, go back. I've constructed that as well. And so if I line my bromines up, we can see that this compound does in fact have a plane of symmetry right here. So compound number 4 also has a plane of symmetry, which means compound number 4 also is meso. So as we looked at each of these compounds using models, we can easily see that molecule number 1, 2, and 4 are all meso compounds. So for me, solving these problems without the models definitely is more challenging. Here is cyclohexane, and I take a look and I see that it is 1,4-cis cyclohexane. And so I redraw the flat ring on that, and I see that there's a plane of symmetry. So I recognize very easily that that is a meso compound. For this compound right here, it's pretty easy for me to figure out R and S. H is going back, 1, 2, 3 priority. So that is R. Here my H is coming at us. Remember that wedge means that it's coming at us and the dash means it's going back. So whatever it is, we flip it because we're looking at the back side of that steering wheel. Here's priority 1, 2, 3. So that looks like it's an R, but it's in fact an S. So we have RS. In order to have a meso compound, we're going to have 2 stereocenters that are the mirror image, which means we have R and S. You can also have SR, that's meso, but this one right here is RS, and it is therefore meso. When we're looking at the Newman projection, then that's a little bit harder for me to see without building the model, because to just look at that Newman projection, it may look like there is a plane of symmetry in it. So if we rotate that front carbon 180 degrees so that the OHs are lined up, we'll see that the hydrogens and the methyl do not line up. And so that's an easier way to figure out if we have a plane of symmetry. So compound number 3 is not meso compound. There is no plane of symmetry. For Fischer projections, if you didn't want to build a model, I'll show you a little trick. When we have a Fischer projection like this one right here, what you can do is take this bottom carbon and rotate it so that we can move the methyl down to here, the hydrogen up to here, and the bromine over to here. So that's an allowed rotation within the Fischer projection. And so you see there then that there is a plane of symmetry. So the bottom line here is this question was so much easier to answer with the model kit than with the structures that are in this 2-dimensional space. So you're welcome to bring your model kit to class. You're definitely welcome to bring your model kit to the exam. And I would go ahead and utilize that model kit so that you can get all of these questions right. Okay, good luck.